Hi everyone, I'm Mamy Ratsimbazafy. I joined Taiko 6 months ago as a zk engineering lead. Previously, I was working on the consensus layer of Ethereum for 5 years, in particular accelerating BLS cryptography on the BLS 12381 curve. And when I joined, one of my objectives was accelerating Halo 2. So Halo 2 is used by Taiko, but also by many other companies like Axiom, Scroll, zkEVM, LurkLab for their Nova backend, and others. And one of the biggest remaining issue is making it fast, which involves GPU FPGA acceleration. We have many companies working on this. Ingonyama, for example, Superscalar, Supranational as well, which did the BLS acceleration for consensus layer. And I think for further innovation, we need to standardize, to decouple the backend and the prover. So let's talk about the agenda. We'll just give you a brief overview of the state of the PSC, so Privacy Scaling Exploration, a team at the Ethereum Foundation. Then a teaser of the end goal, how to go there, and what's left after this one. And then some Telegram, Discord ideas for how to collaborate if you want to join the effort. So, state of the code base. As I said, we have many users, coprocessors like Axiom and Ezekiel, compiler and high-level frameworks like Lurk and Powder, and rollups like Scroll and Taiko. On the hardware side, we have so Halo 2 KZG with a couple of, let's say, proof of concept for hardware acceleration, some that were using code for Matter Labs, the Bellman accelerated code, others that were created in October from Superscalar or Delphinus Lab on the Zcash side. Yeah, one thing when I say Halo 2, it's Halo 2 KZG, the one used by PSC, but Zcash has the original library that uses IPA for commitment. And we also have Arcworks that so far has been the target of GPUs and FPGA acceleration. How to make them all work together in a nice land filled with unicorns, that's the goal of the talk. On the software side, I want to highlight a bit some of the efforts I did. So on the Halo 2 KZG 187 issue, I've outlined 7 steps to go from current Halo 2 speed to state-of-the-art. We have recently had zcalc and a talk at zk Summit 10 about benchmarking snarks. That said that GNARC is the fastest MSN provider benchmarked, and it provided above 10 times more speed than Halo 2 KZG. And besides that, I have also my own personal library that I wrote from scratch in the past 4 years, called Constantine, that reaches the same speed as GNARC, or even faster, like up to 40% faster, but it's only on a small number of points that are applicable for EIP 4844, for example. This is a slide that I shamelessly stole from the talk at ZK Summit 10 that highlights GNARC and Arcworks and other implementation. Just say that GNARC is below, and since time, that means it's the fastest. Now, why do I still talk about software in a GPU and FPGA and hardware acceleration conference? Because I think software still has potential. GPU renting cost is quite high, and we are in competition with AI startups that want to gobble up all the GPU available. We have also GPU embargoes, so some of the cheap providers are in China, like Tencent, Alibaba Cloud, and they can't give access to the latest NVIDIA GPUs. The other thing is that we can still have access of many threaded CPUs, like AMD EPYC CPUs. You can have 384 threads if you use 2 sockets of the latest EPYC. And on Xeon Platinum with 8 sockets, you can get up to 960 threads. is there someone using this, that much compute on zk to see how inexpensive it is compared to GPU? I don't think anyone is using yet. And how would I use this today with my own library or with Gnark or Arcworks over? Well, so far, the Halo 2 KZG and Arcworks library are using parallelism at only one level. But you have many more levels of partitioning points. So MSM level partitioning, where you have 1 million points and you compute on 500,000 points on one side, 500,000 on the other side. Why don't we do this? Well, because if you split, you don't benefit from the multiscalar multiplication, which makes the complexity grows by n divided by log n. So we try not to do this too much. Then there is window-level parallelism that everyone uses it because it's the simplest one. And there is bucket-level parallelism, which provides the more parallelism possible because you have millions of buckets if you have, for example, 4 million points. And the issue is that you need sorting because otherwise you have collision and data races. So, in terms of software feature developments, besides what I talked about, there are also specialized MSMs that are specialized for lookups, or for example, for Ketchak hashing functions that worked at the bit level. And we have an example of Halo 2 202 done by Axiom that accelerated Ketchak implemented at bit level by 40%. Plus, we also have prover-level parallelism, where, for example, for EIP 4844, for batch KZG commitment, you have free scalar, multiscalar multiplication that you can compute in parallel, and those will be parallel as well at free level, and then you have 4 levels of parallelism that you can use for acceleration. Now, the end goal. I guess everyone knows this XKCD. There are 14 competing standards. We need to develop one universal standard to cover everyone's use cases, and then there are 15, except there are 0 at the moment, so hopefully we can kick the ball and get this started. Concretely, we want to dissociate the proof system from the computing backends because provers are always evolving. We had KZG commitments-based provers, IPA-based prover. Now we have GKR prover with some checks. And we use MSM's FFT primitives that hardware provider can target without being worried about all the prover changes. Now, also hardware accelerator, they want to minimize the work done and have multiple prover for a single, with a single code base and just very small adapters, maybe 50 lines of code, just to make sure that it works for everyone. This reduces maintenance costs, reduces the bug surface, and they focus on their specialty. And proving library can focus on the high-level part, lookups, optimization, etc. Plus, they can do differential fuzzing and benchmarking because, well, in the past couple of months, we see a lot of benchmarks, but it's very hard to compare. Still, everyone says it's apple to oranges, and we haven't had Twitter fights. And in the end applications can pick the backend, hardware acceleration backend that they want. Maybe they want AWS. Maybe they want to work on GPUs, maybe on FPGAs. It's in the control of the end applications instead of the proving library like Halo 2 or Arcworks. How to get there? I made a proposal 2 months ago called, since this talk, Acceleration Abstraction Layer. It proposes an encoding of field elements, of elliptic curve G1 elements, optionally an async API to issue multiple MSMs or FFT. And how it does this is all FFT and MSM are prefixed with a context parameter called engine. And that's where all the nitty-gritty stuff and the implementation details go, like number of cores, so you can read your environment parameters, or the GPUs to issue the multiscalar multiplication or FFT2. Thankfully, there is not much difference between Halo 2 artworks. I mean, everyone is using Little Endian for limb endianness because all GPUs, AMD, and NVIDIA, Apple are using Little Endian. Also ARM, x86, RISC-V are using Little Endian. So it just makes sense. And because we're talking about proving, usually, well, Halo 2 is using period-friendly curve, so everyone is using Montgomery representation. Now, for stacks, we can, of course, use a canonical representation for this. The ABI was inspired by accelerators for image processing and machine learning. So I used to be a data scientist and a deep learning developers. I've used CUDA, cuDNN, 1DNN from Intel, OpenCV HAL, a hardware abstraction layer, which is very much in line with what we want to do, and also the Windows kernel APIs. The main difference is that those sometimes ask you to first query to get the size of memory to allocate, and then they tell you allocate the memory. I think this is going a bit too far, so for now I've not done that, but I'm open to suggestions. And as I said, engine context, and maybe at one point we'll add an optional operation descriptor if you want to cache, for example, your trusted setup, and you don't need to recompute it at the beginning of the MSM. I've looked into the changes that are needed in Halo 2. Best FFT, the FFT compute appears twice. The only issue is that there are also coset FFT, and I have yet to figure out what API and ABI to get for those. And best multi-exp. I really don't like the multi-exp name for multiscalar multiplication. It goes to additive versus multiplicative notations, but it appears only 9 times. Thing is, those propagate to everywhere, so we need to change everything. Now, what's next? For now, I focus on the sync API because everyone is doing sync call to multiscalar multiplication, but in the future, async API, so you just call MSM async, a bit like CUDA, memalloc async, and then you just wait on this, and you can compose as you wish. The caching abstraction I mentioned, and then some of the hardware acceleration team, like Ingonyama, said that, well, just MSM might not be enough. We might need KZG commitment level acceleration, or even Planck level acceleration, so that everything is done in GPU. We can explore that later, but let's get a working group started first, and go forward from this. Now, collaboration. You can read my issues 216 on the PIC codebase first. There is also Superscalar that did their first proposal. And you can talk to me on the side. We can discuss if we create a Telegram group or a Discord channel. And I invite all software libraries, hardware providers, and end users to talk to me afterwards. Thank you very much.